So welcome back. This is the lecture about map and MPE inference. So when we make a map or MPE query, we are interested in finding an assignment that has the highest probability. And we haven't seen this before a few times in this course. I guess the first time that we discussed map and MPE queries, we were talking about classification. And when we do classification, we are interested in finding the class value that has the maximum probability. But we haven't seen this topic before too. I guess the second time we discussed that we were discussing the Viterbi algorithm that we use for hidden Markov models and for conditional random field. And in this case, we were looking for one assignment with highest probability for all the hidden variables that we had in the model. And we also discussed this topic once more when we were talking about the Markov networks and we were filtering images. And in this case, we came out with a solution that was a stochastic algorithm that looked for a map assignment for an image. So this map assignment would be the filter version of the image. In this case, because the search space was so large, we wouldn't be able to come out with one efficient exact algorithm. So this stochastic search was an approximate answer to the query. So in this lecture, we're going to discuss more about mapping MPE inference and going to formalize a few concepts. We're going to see how we can work with different algorithms that we haven't worked before, like variable elimination or belief propagation in the context of these maximum probability queries. So in this lecture, we're going to discuss two classes of queries. The first one is map, maximum a posteriori hypothesis, and the second one is the MPE, the maximum a posteriori explanation. So the names are very similar because they're actually very similar types of queries. We can understand the MPE as a special case of map. In both cases, we are interested in finding assignments with the highest probability. The difference is that the map tends to be more complicated because it will involve a step of variable elimination, where MPE does not. So I'm going to study MPE first because it's going to be simpler, and I'm going to study the more general case of map later on, and we're going to see the differences. And we will discuss a few approaches to solve this problem. One is based on variable elimination, and we haven't seen this before in the case of the Viterbi algorithm. So I'm going to discuss how is this variable elimination algorithm for a more general case of inference, and we're going to see how the Viterbi algorithm instantiated to this more general algorithm. But we're also going to see other different types of algorithms, and in particular we're going to discuss the systematic search that basically going to use a depth-first approach to find the MPE or map query. And finally, we're going to briefly discuss how we can adapt the belief propagation algorithm to the case of map and MPE queries. So we're going to use this example during this lecture. It's a Bayesian network for a certain medical condition. So we have a population that have a little bit more males than females. So more males than females, so we have 55% males and 45% females, and that information is here in the variable S. And we have a condition, and this condition is dependent of the sex. And that happens because this condition is a little bit more likely in males than in females. So we can look at here at this table, and we can see that 5% of the male population has the condition, while just 1% of the female population has the condition. And we have two tests for this condition. The tests are T1 and T2. So there are these variables here, T1 and T2. And the test T2 is a little bit more effective on females. So we see here that the true positive for females is 95%, and the true negatives for females is also 95%, where for males they are equal and they are 80%. And the test T2 it's equally effective for males and females. So we can see here that the variable sex here, the variable s, is not in this conditional probability here, and we have 8% for true positives and 8% for true negatives. And we also have this variable a here at the bottom of the Bayesian network, and this variable is saying if the two tests have the same outcome or different outcomes. So it's going to be a binary variable that's just yes and no, and in the case that we have the same outcome for tests and it says yes, so we're going to have this deterministic CPT here indicated that's 1. But in the case that we have equal values for the test and the variable says no, so that's not correct, so it's going to be 0 probability and so on. Okay, in this example, we can think that we can partition the population into 4 groups. If we look at the variables S and C, that is sex and condition, we can think that sex we have males and females, and conditions we have yes and no. So we have these 4 possible groups of males that have or not have the condition and females that have or not have the condition. And let's suppose that someone takes both tests and the tests come with the same results. So we have this evidence that A equal to yes. So what is the most likely group that this person belongs to? This is a type of a map instantiation, and in this case we are looking for the most likely instantiation for the variables S and C, given A equal yes as evidence. And in this case we say that S and C are called the map variables. If we compute this query and see what will be the result, it is unsurprisingly the case that the sex is male and the condition equals to no. And we know that comes from the fact that the males is the largest group in the population, and also because the population, the disease is prevalent only 5% of the male population. So S equal male and condition equal no will be the most likely assignment, and it has a probability that almost 50%. And we can use variable and factor elimination to compute these map instantiations, and the approach is actually very simple. What we do is to make a query that involves all the map variables, and we look at the final factor and see which entry has the highest probability. So in the case of this example, we could use variable elimination or factor elimination to compute one factor that has the probability of C and S. So we have the variable S, we have the variable C, and they have the probability of S and C or C and S here, right? And in this case, what we are interested in, not in the probabilities, but into the assignment. So we're going to look for one row here that have a certain value for S, a certain value for C, and has the highest probability of all probabilities that we have in the table. Of course, this assignment may not be unique. We may have 2 or more assignments with the highest probability. And the problem with this approach is that it is exponential in the number of map variables. So S and C here are the map variables, and we know that the size of this table is exponential in the number of variables. So if you have a large number of map variables, we will have an exponentially large table, and we need to scan this table in order to find the entry with the highest probability. So our objective in this lecture is to present some algorithms for computing map and also MPE instantiations that are not necessarily exponential in the number of map variables. So there is one special case of map that we call MPE, and in this case the map variables they contain all the unobserved variables that we have in the network. Just to make it a little bit clear, in the case of the map queries, we have 3 sets of variables. We have the map variables that are in the query, we have the evidence variables, and we have the hidden or unobserved variables. And the task here will involve to eliminate these unobserved variables using inference. So we're going to have to sum out those variables and eliminate them. In the case of MPE, it's a little simpler because in the case of MPE, we have just two sets of variables. Because the query variables, the map variables, will involve all the variables that we have in the network. We will not have the unobserved variables, we won't have the map variables and the evidence variables. So in this case, we have just two sets of variables, and that's going to make the task of inference a little easier for us. So in the case of our example, if we want to compute an MPE query, in this case, we will have A, that's A equal yes, that's going to be our evidence, and all the other variables will be map variables. In this case, that would have 16 groups instead of 4, because we have males and females that have or not have the condition, and they also have 4 possible outcomes for the 2 tests. So if we compute this map instantiation for this MPE query, so the results will gonna involve the 4 variables S, C, T1, and T2, not A because A is evidence, and the answer is this one, right? It's going to be S equal to female, C equal no, and both tests will be negative. So this has the posterior probability of around 47%. So this case of map is known as MPE instantiation, and it tends to be a lot easier to compute than the map queries because it will not involve the elimination of variables. It's important to note that MPE tends to be a lot easier to compute than map, but MPE is not the answer for map queries. So if we look at this example, and if we project this MPE answer into the variables S and C, or in this case we just take part of the instantiation, we're going to so this part here, S equal female and C equal no, it is not the same answer that we got for the map query, that we got S equal male and C equal no. So it's not the same answer, but because MPE queries are easy to compute, sometimes when the map query is too difficult to compute, we use the MPE as an approximation for the map query. But it's important that the answer is not always the same. So it can be an approximation, but it's not the exact result. Okay, so let's get started by computing the MPE assignments. And in this case, remember that we don't have a hidden variable. So everything that we're going to have are the query variables, the Q, that also known as the map variables, and also the evidence variables. And these are the 2 sets of variables that we have from the network. And our objective is to compute the MPE probability, that we're going to use this notation here. And the MPE probability is basically the maximum probability that we have for all possible instantiations of the query variables Q and evidence E. And we are frequently more interested in the MPE instantiation than in the MPE probability. And the MPE instantiation are the values of the variables in the query. So in this case here, we're going to define as the MPE instantiation as the argmax. So I'm interested in what are the instantiations for Q that have the maximum probability. Notice that we are talking about this probability of Q and E, and not the probability of Q given E. That is basically the same thing, because we have this result here, that is the probability of Q given E is the probability of Q and E divided by the probability of E. So what we are talking is that it's basically going to be a normalization step. If we have a table that mentions the probability of Q and E, so we have a table like this, right? So we have all the query variables like Q1 and Q2 and Q3, and we can also express here the evidence, but they're going to be constant, E1, E2, and so on, and we have the probability here, right? And so we are looking at the assignment here that has the maximum probability, and this guy is going to have a certain probability P here that is the highest of all probabilities that we have. And if we sum all those probabilities, we have a z here. And if we divided each entry by z, right? The maximum P here that is unnormalized will be also the maximum after the normalization step. So as it will not change the result, so it's going to be simpler to compute the probability of Q and E and take from there the maximum or the argmax among all possible instantiations. So this is our example. So the Bayesian network and also all the parameters that we have here, the conditional probabilities, and we're going to use this example to compute the MPE instantiation using variable elimination. But before we do that, let's suppose that we decide to do the naive approach and we're going to compute the joint distribution over all variables and look at what is the assignment with the highest probability. In this case, we would have a table like this. So this is a large table with a joint distribution over all possible variables that we have here. And in this case, because the table is large and also because A has a deterministic CPT, we are omitting some rows. There are the even rows because they have a 0 probability in there. And if you look at this table here, you're going to find in this row here, the row 31, the assignment with the highest probability. So this is going to be our MPP probability. And the MPE assignment, in this case here, we are assuming no evidence at all, right? So we are considering all variables. And the MPE assignment is this one. It's female, no for the condition, and the two tests are negative, and yes, indicating that the two tests have the same outcome. So in order to compute MPE and MAP queries, we need a new operation over factors. Actually, it's not new because I haven't seen this before, and we have even implemented that in the tutorials. That is the maximization operation. So the maximization operation will replace the summation operation in variable elimination. So the algorithm for variable elimination for compute map and MPE queries will be very similar to the variable elimination algorithm that we've seen before, but they're going to replace the sum out operation by the maximization out operation. So I'm included in this slide here just to make it very clear. So what we have to do is to look at entries that match the assignments, and you're going to select the entry that has the maximum probabilities. So let's suppose that we are interested in eliminating variable B here. So we're going to find one assignment that has A0 and C0, and this assignment is here. And we look at all possible values of B. So we have B0 and B1. So in this case, the variable is binary, so we have just two possible values. And so we're going to compare two rows here. If B had three variables, we would have to compare three different rows and so on. So in this case here, we're going to take the maximum between 7 and 0.2. In this case here, it's 7, right? And we continue doing that. Look at that, and not even mentioning probabilities here. The numbers are not between 0 and 1. It's because this operation is valid for any kind of factor. We can even transform our probabilities into log probabilities and compute this maximum operation that will also work. And that actually is the standard technique, because typically you're going to find the maximum among a large set of variables, so we need to multiply them, and we can incur in some underflow. So it's very common to transform the probabilities into log probabilities. I've having seen before in different situations, for instance, when we were discussing the naive Bayes classifier. And we keep in doing that, right? So here the colors are indicating the rows that we have to compare, and we take the maximum between them. So when we maximize out a variable B, for instance, from the factor phi, what we get is another factor, and that does not mention variable B anymore. But more important than that is that the new factor agrees with the older factor about what is the MPE probability of the assignments. So what we do when we are computing the MPE by variable elimination is to maximize out all the variables that we have in the query until we get the trivial factor. And that is going to be slightly different from what we used to do when we were starting working with a variable elimination for inference, because working with variable elimination, we eliminate out all the variables that are not query variables. Now here, we're going to maximize all the variables that are in the query until we get a trivial factor. And you're going to see that this process will give us the MPE probability, but we also extended this approach to give us the MPE instantiation. So it's going to give us the complete answer, probability, and also instantiation. Two important properties for maximization that are also valid for the summation is the fact that the maximization is commutative. So it means that if you want to compute the maximum for a certain variable x1, so we're going to eliminate two variables, x1 and x2, from the factor phi. And if we invert the order that we eliminate the variable, so if I eliminate first x2 and later on the x1, is going to be the same result, right? So one thing is equal to the other. So we can talk about eliminating x1 and x2 without specifying an order for that, because the results are going to be the same. And also, one important result here is that we can do the variable elimination process, because when we are maximizing out a variable x from two factors, phi1 and phi2, but phi1 does not mention the variable x, so we can remove the phi1 from here and place it there. So it's going to be equal to phi1 times the maximum over x for phi2. So in this case, we can remove the factor phi1 and can eliminate the variables only in phi2. So we can do this localized elimination of variables, so they're going to be more efficient than multiplying first the factors together and later on removing the variable. Okay, so this is the algorithm that we call MPE-VE. VE is the variable elimination. So what we have here, we have a Q, there are the variables in the network. We have pi, that is the elimination order over Q. And we have S, that are going to be a set of factors that are matched to the evidence. So when we talk about this guy here, we are talking about the factors that we have in the network matched to the evidence. So we are eliminating all the rows that do not match to the evidence. All right, so what we do is basically variable elimination. So we'll go through all this loop here. We're going to operate all variables in Q. Remind that MPE, the Q variables are all variables that we have, but the variables in the evidence, right? So you're going to do a process of elimination for all those variables. And we do this in two steps, as we are used to. First, we multiply all the factors that we are calling here the phi k that belongs to S and mentions the variable pi I, right? So, for instance, in the first iteration of this loop, we're going to take the first variable, take all the factors that mention this first variable, and multiply them together. We are calling this sigma I. This is the first step, and they have a second step that is the maximization. And in this case here, we create a new factor that we are calling the tau I. That is the maximum of sigma I for the variable pi I. So we are removing the variable pi I from the factors that we just multiplied. So when we finish with that, we can eliminate all the factors phi k that we multiplied, and we remove this from the set S, and we introduce this new factor tau I, replacing all the factors that we multiplied. And we keep on doing that until we finish with all the variables in Q. At the end, like what happened with the factor, the variable elimination process, we may have one or more factors in S, and they all be trivial factors. We just multiply all of them together and return these to the user. So we have a few notes here. So all factors are eliminated, leading to a trivial factor. And that is different from what we are used to that we are used to eliminate only with variable elimination that we learned in the variable elimination lecture, right? So we are used to just eliminating the hidden variables and keeping all the query variables. Here we're going to eliminate all the query variables. And remember that the query variables are all variables in the network, but the ones that are associated with evidence. So this phi e here is the factor with the rows, so the factor phi that we have in the network with the rows that do not match the evidence here, remove it. If we are doing pruning, we can only do edge pruning because we cannot eliminate any variables here. All variables are important to the answer. Remember that Q will have all the variables that have in the network, so we cannot prune any of them. And the complexity of this algorithm is the same complexity as variable elimination, so it's basically the same algorithm, but with just one small modification that we are changing the summation operation by a maximization operation. So yeah, we can expect that the complexity will be n times an exponential in W, where n is the number of variables and W is the width of the elimination order. All right, I think that is good for this first video. We'll continue in the next one. We're going to take one example and run this example step by step to check if we are having the correct understanding of the method. So see you in the next video.